Okay, today is December 5th, 2011. We're on lesson 7.7. These are the formulas you're going to be using for the next two chapters. Now, I wanted you to define congruent and similar. And we're going to essentially kind of make sense of those two words from example 1. I have two triangles. I need to know if they are congruent or similar. Does anyone know the definition of congruent? What is it? Okay. Are these two identical in size and shape? Yeah, that's right. So, very simply, those are congruent triangles. That means their angles are the same, and their sides, we'll call this side A. This is angle A. Okay, let's get used to naming our triangles. Angle A. Sorry, they technically should have different letters. Don't worry, we'll get to it. That's D. We'll call this B. Angle B. E. Side E. And this will be C and C, F and F. Okay, so there's a second lesson I put in here. These are congruent. In other words, angle F is equal to angle C. Side F is equal to side C. So the distances are the same. Angle B is equal to angle E. That's an angle symbol I'm using. Side B is equal to side E. And finally, angle A equals angle D, and side A equals side D. Okay? So everything in these two triangles are the exact same. What's important, I want you guys to notice, is whatever I called the angle, I used an uppercase letter. Okay? And the corresponding side to that is the side that is opposite of that angle. So if this is angle A, the opposite side is side A. And I use lowercase letters to represent our sides. So angle B, opposite of that, is side B. Angle C, opposite is side C. E, F, and D. Okay, the next triangle, we're going to compare. Do these have the same angles and side lengths? They have the same angles. I'm going to tell you that. So these would be considered similar triangles. Now, I'm going to do the naming of these two triangles a little differently, because there are a couple ways you can name a triangle. Now, the way I showed you above will become very helpful for our trig. But today, what they are going to probably do is they're only going to use three sides of a triangle. So let's say they call this G, H, and I. And this is maybe J, K, L. So they've given us points, also known as the angles. Okay. Now, in your book, they're going to represent them a little differently. What they're going to say is when they name an angle, they're actually going to use all three letters of the triangle. So if they're referring to angle G, which is this angle right here, they're going to call it angle I, G, H. Okay, let's actually zoom in a little here. So when they refer to angle G, which is the one we have in blue here, they're going to call it either angle, and they use this symbol, I, G, H, or they can refer to it as angle H, G, I. Now, normally they do in alphabetical order, okay? What is important is that the G here falls in the middle. Because what they're saying is they're starting at this point, drawing a line and drawing a line, and creating this angle in between. Or they start at H, come over and come down, and they're creating an angle in between. I'm having a lot of trouble writing today. Okay? So, we have our angle G. Their angle I, they would call it angle GIH, or angle HIG. Okay? Again, the I falls in there. That's our 90-degree angle. Yeah, usually. And finally, angle H would be angle IHG or angle GHI, depending what their starting point is. But essentially the reason they're doing that is because if I start at point I, go over to H, and then come up to G, I formed an angle here, and that's the angle right at H. Okay? So it's important we can distinguish between those. Now, what I want us to do is I want us to get the equivalence here. So what would the equivalent angle be in our similar triangle for angle G or IGH? What would the similar angle be? LJK. And the reason that is because they started at I, went to G, and then H. So they start here, go up to G, come down to H. To have that similar angle, these angles are the same measurements, LJK. Okay? We've gone through the same motion they have, which also means angle HGI would be considered what? Yes. Okay? JL. Those are the equivalent angles. Now, technically, all these angles have the same measurement. Let's do the next one. Angle GIH would be considered what? JL. Okay. And angle HIG? KLJ. Good. Finally, angle IHG. LKJ. Remember, they started at I, went to H, so we'd start at L, go to K. And finally, angle GHI would be JKL. Now, everything in red actually has the same measurement. Everything in black has the same measurement. Everything in blue has the same measurement. Now, if we're referring to sides of this triangle, okay, there's two options here. Scroll up a little. Now, here's one side of the triangle. I'm going to call it, stuff's moving. I'm going to call it GH, okay? And GH is also known as HG. Again, it's normally in alphabetical order, but it doesn't matter. When I go from one point to the other, the distances are the same between those two, okay? Another side we could work with, actually, you know what? I'm going to change that color. I'm going to make that in black. See if anyone can make the connection. Why am I putting it in black? The reason I'm doing this is because it's opposite of our black angle, okay? Our blue side, we're going to call line segment IH or HI. Again, those distances are the same. And finally, our last one would be GI, Joe, or IG. Okay? Those are the same. Now, the sides they would be referring to on our similar triangle, let's go down. GH would technically, if we're following the same pattern, would be JK. Okay? Yes, that's right. Which is also equal to KJ. But these are not equal. Okay? And that's why they're similar triangles. Those sides do not equal each other. Clearly, the similar triangle on the right has much longer sides than the one on the left does. Okay? Same idea. IH would be considered LK, which is also equal to KL. But again, they're not equal to those other sides. And finally, JL. Finally, JL, which is also equal to LJ, is not equal to the other side. So that's why these are similar triangles. The angles are all equal, but the sides are not the same length. Okay, in this question, we have points. This point is X. The point directly below the person here is point P. And point directly at the top of its head is point N. We also have directly under our math monster T, and directly above is point E. Now what's important about this is we can actually create two right-angled triangles out of this. Okay? So we have one right-angled triangle going from P to N and to X. The other right-angled triangle goes from X to E to T. Okay? So I've created two right-angled triangles, which is actually quite important for the next two chapters, making sure we can create the triangles. Now these two triangles, first I have to decide, are they congruent triangles? And I'm going to highlight them. This is our first triangle. And our second triangle. Our second triangle here is in green. So we have our two right-angled triangles. Are the green and yellow triangle congruent, or are they similar? They're blatantly similar because the sides are definitely not the same length. Now I'm quickly going to recreate the two of them. I'm going to shrink the other one down a little. So these aren't to scale, okay? But we do know they're similar triangles. And what I'm going to do is very important. I'm going to name them. This will be considered point X. This would be point P. And this is point N. Now I know this isn't to scale of the green highlighted one above, but this is our X, T, and E. Now what I want us to do is make some statements about this triangle. First of all, I would like to know angle N, X, P. What angle would that be equal to in the other triangle? Yes, angle E, X, T. Very important, the X is the middle letter in both of those, okay? How about angle XNP? Would be equal to XET. And finally, angle XPN would be equal to angle what? Anyone know? XTE. Good. Okay. One more thing I do want to go through. I'd like to talk about the sides of this triangle. Sides of these two triangles. Is side XN equal to side XE? Are they equal sides? Nope. Is XP equal to XT? Nope. That's why they're similar. And finally, what's our only other option? PN is not equal to TE. Good. Okay, so in this question, I have two similar triangles. Okay? We know they can't be congruent because our corresponding sides and then quickly go over them. These are corresponding, and these are corresponding, are not equal. Now, how can I actually prove that this is a similar triangle? What kind of property do I use to prove that the angles are the same? Renee? Yeah, which angles? Yeah. Here? No, here. This one here? Okay, what is that angle rule? Anyone remember? These are opposite angles. Okay? So, because these are opposite angles, we have two straight lines going. Opposite angles. We know that those angles, and I'm going to name them, angle DCE is equal to angle A, or actually, I'll say B, just so it kind of follows the same pattern. BCA. Okay, we know those angles are the same. What other angles can we prove are the same? Anderson. A and E, and how do you know they're opposite? Yes. This rule is alternate angles, or you guys might know it as a Z. Okay? This side and this side are parallel lines. Okay? So I'm going to put that in there. I actually should have put that in there to start. Those two are parallel lines. So when a line crosses through them, we have alternate angles. Those are alternate angles. So in other words, angle DEA, sorry, we'll call it DEC, so it's in the triangle. DEC is equal to BAC. We know those angles are the same. And what about our last two angles, which are B and D? We know two, that's right. So we can prove the last one's going to be equal if the first two were. By logic, by elimination, the other two have to be equal. We know it's going to be a right angle because the one below it is a right angle. We can also, again, use our alternate angle rule. Okay? We have two parallel lines, and we have a straight line. Well, it's perpendicular in this case, going through it. So again, we have our alternate angle rule. Or by logic, because the first two are similar, we know the last one has to be, or sorry, the same. So that means angle CDE is equal to angle CBA. Okay. So we've proven those are the same. That's nice. What I want to do now is I want to talk about the ratios between the triangles. If they're similar triangles, essentially their angles are all the same, but they have a different ratio to each other. We know that one side is longer than the other on the two opposite triangles here. Oh, that's one else. Here we go. So I'm going to name a side here, and I'm going to call this side CE. Okay? And I'm going to compare it to what side? Does anyone know? CA, that's right. This would be essentially the equivalent side when I twist the triangle around. So it's going to be divided by, you know what, I'm going to get rid of the line on top so it doesn't confuse you. But CE and CA are equal to. Now, I'm just going to show you that quickly. What they're saying here, when we twist the triangle all the way around, yeah, it is going very slow. So if you notice, holy, as we rotate it very slowly, we realized I went way too far. We realized our AC was equal to, is this still going? Boom. I can't figure this out. Okay, so now what's important is my side CE is 25. So, CE was 25, AC was 5. Let's reduce this fraction. What is this a fraction of? That's right, if we go to unit value, it's 5 over 1, which is known as a ratio of 5 to 1. So if we're going from the larger triangle to the smaller one, we're going down at a ratio of 5 to 1. Let's do the other sides also. So we had CE. Let's do ED divided by, what did I do? We were using side ED. AB, which is a ratio of 20 divided by 4. Works out to be the exact same ratio as above. Again, 5 to 1. Right now we're just going through proving these. And finally we have DC divided by BC, which is 15 to 3, 5 to 1. We have a ratio of 5. Whoops. 5 to 1. Now, what was very important, if you guys notice, when I set this up, I started with the larger triangle on top of the fraction every time. Had I done it the other way, you would have had a ratio of 1 to 5. You must be consistent when you set these up. If you start with the larger triangle on top, you must do that every time. If at some point you switch it around and put the bottom one on top, you'll end up with a ratio of 1 to 5, which won't make sense because it won't be equal to our other ratios. Page 334, 710, 13, 14, 15, 16 is